we're back at my school, and we have an early start today. So, yeah, early start today. And yeah, I got a new marker. It's great. So, you guys can probably see it better now. Let me just reduce the camera. Okay. So, to conclude this course, what we're going to do is discuss about Bussy Spaces. Bussy Spaces. Oh, okay, ink. Now you guys can probably see that. That's great. So, I said in the beginning of the course that that we were including Z of C, not only Z of C, or we're using Z of C as our basis for our mathematical logic, but we're also using our axioms from femboyology. And I said that the most important axiom we're using from femboyology is the axiom of the Bussy set. And what this axiom states is that for any two sets that are tangentially related or directly related to the Bussy contains an intersection which is called its Bussy set. So if we have two things that are completely unrelated to each other, but they do share something common with the Bussy, or they're both tangentially or directly related to the Bussy, then there is a set which is their intersection, which is their Bussy set. So for all xy that are tangentially or directly related to the Bussy. For all xy that are tangentially or directly related to the Bussy, I'll just point. There exists a set which is blackboard boldface B, such that the x, or the intersection of xy, is precisely defined to be that B. And this is the B of xy. This is the B of xy. Or in a more discrete way, we can describe as this: B xy. Or this syntax over here, or you can use this bracket, this subscript bracket notation. Okay, so that's a Bussy set, and I want to say, or we should establish now that we know that every femboy has a Bussy, right? We all femboys have a Bussy, so that's a very obvious fact and a very fundamental statement. So that's one additional axiom we're going to be adding to our list of axioms. And that is that axiom of the femboy Bussy. And it states that every femboy which I will call small f, can contain a Bussy. And since this axiom is evident throughout the entire, our entire literature, our entire curriculum, we can conclude from this second axiom that all possible intersections from our set of universal femboys, which is, well, F, mathcal F, this a theorem. Call it theorem 7, or theorem 6. No, 7. Let me check my notes. I did discuss about the Banach-Tarski paradox in the previous video, so I need to refresh myself on this. Yeah. Hold on a second. 10 or 6. Yeah, it's 7. Theorem 7. Theorem 7. All F, all pairs of femboys, which I will call this ordered pair F1, F2, in our fundamental underlying space of femboys F, mathcal F, excuse me, or its topological space, or open sets, or open intervals, F1, F2, inside the topology of F, contain a Bussy set. The proof is obvious for this because once we establish our axiom of femboy Bussy, right? We know that every femboy has a Bussy, and since that fact is evident, it's easy to conclude that all pairs of femboys contain a Bussy set. So I'm just going to write the proof here. I know it's trivial, the proof is trivial, but I'll just write it down. Proof. Proof. Use axiom of F Bussy. Then use a box to end the proof. So what this is saying is that if we have two femboys inside, if it's a regular, field or space of femboys, right? If we have two pairs of femboys there, so another pair, or just a collection maybe, it can be a set, just a small subset or subspace of that, space, field, or structure of femboys, or maybe just a set. Any two femboys, we're going to take the intersection of, contains a Bussy set. They have a Bussy set. And so lemma 1 from this theorem is this. So I'll erase the proof. The proof is trivial anyway. We just use the axiom of the femboy Bussy. So lemma 1, lemma 1 for this theorem. The Bussy set of the ordered pair F1, F2 is precisely the intersection of F1 and F2. So I'm gonna write the Bussy set here. So the shorthand. The Bussy set. F1, F2 is of the ordered pair is precisely their intersection. And stay in our femboyology course. So that's that. So that's basically our a recap of what the Bussy set is. And the Yaoi set is essentially the same thing, but instead of the Bussy here that we're talking about Yaoi themselves, right? So if two sets or two elements or open sets or elements or intervals or subsets of a given set are directly or tangentially related to Yaoi, then we say that their intersection is just the Yaoi set. And I know I didn't go in depth in that in femboyology, but any instructor that will dig deeper in femboyology too will probably discuss that. So let's jump on to the main event of this lecture, which are Bussy Spaces. Now, before I discuss Bussy Spaces, I need to discuss about what they are and what they aren't. So a Bussy space is not just a vector space, okay? It can also be a topological space. Bussy spaces are, to be honest, they are two things. They can either be a vector space, or they can be either a topological space. Or they can just be a field of scalars, and then, the scalar is just some sort of magnitude on the spectrum for femboys, So if I construct a spectrum of femboys, and then we have some number that indicates what exactly is the position of the femboy on that spectrum, we can think of a Bussy space as a field of scalars, or a field of integers or numbers that signify a position on that spectrum. If it's a vector space now, we're thinking of Bussys now, or Bussy sets, as vectors. Since of course it's a vector space, it only has vectors for elements. We can think of them as a topological space. Obviously, topological space. And the neat thing about topological space is that we already established in the last two lectures, or last three lectures, is that if we have some active homeomorphism between our given topological space and REL, then we can say that they are some F manifold, a manifold. Since n, the natural numbers, are a subset of REL, and n is a subset of R, so we're essentially mapping onto a subset of R, and so we have ourselves a manifold. And we talked in that video, I talked about femboid donuts. The donuts. So yeah, and how this can be thought of as a femboid, right? Now, consider the intersection between two F manifolds. So consider the intersection between this and some other wonky manifolds, say like this. Maybe it's a potato, or maybe a saddle. Let's make it a saddle. A saddle is a manifold. Or maybe a Mobius strip. Let's use a Mobius strip. Let's use a Mobius strip. So this is a. Okay, it's a bit difficult to draw a Mobius strip because I don't quite know how to draw one. That right? Yeah, Mobius strip. Mobius strip. You just grab a piece of paper, right, and okay, so let me just demonstrate it. So you guys know how if we have a piece of paper and then we wrap it around itself, we get ourselves a cylinder. We get ourselves a cylinder. So two sides, one inside and outside. But if we have a strip of paper instead, so I'm gonna wait, hold on, let me get this. So if I have a strip of paper, something like this. This is not paper, it's cloth, but if I do this normally, right, we get a regular cylinder, inside, outside. A topological, a non-orientable manifold, which is non-orientable two manifold, which we call or one manifold, which we call the Mobius strip, and the Mobius strip, is if we twist it. So we twist it one side and then connect the ends, and so we get a one surface shape. So we travel along it. We end up traveling both sides. So that's a Mobius strip. And okay, so let's consider a Mobius strip that's some sort of F manifold. Not orientable, but still a manifold nonetheless. So we can make some clean projection from our current plane onto R. So okay, I have a manifold, and then let's say that it's tangentially related to the Bussy. And let's say that this F manifold over here, this donut or femboid donut, let's say that this is a 2F manifold 2 FT2. Let's say this is FT2. I'll just call it FT2. 2 manifold FT2 is a mouthful. So let's say that this is FT2. And then this is some Mobius strip. This is a Mobius strip. And then we have an FT2 manifold. And let's say that both of these guys are tangentially related to the Bussy. So take the intersection of both of them. And then we got ourselves some topological space. This is some topological space B of FT2. And this Mobius strip, I will call it M. Let's call it M. Oops. Called M. Yeah, it's called mu. So this is a topological space, and since both these guys are tangentially related to the Bussy, we can conclude that this topological space over here is some Bussy space, or set that's a Bussy set. But since it's an intersection between two spaces, we preserve the structure of each space or each topological space. So these two are mathematical structures, right? They have some underlying structure on them or some rule on every single thing here, right? The thing about these rules is that when we combine them or take an intersection between them, that's non-empty, a non-empty intersection. So I'm going to say that this is non-empty. So if we take some non-empty intersection between these two topological spaces, or any topological space in general, then that intersection or that union must be a topological space, because we're taking that intersection, that non-empty intersection, as something that's part of two topological spaces. So like taking a piece out of bread, right? Taking a piece out of combined loaves of bread or combined dough to make bread, we have something as bread, right? So likewise, if we take something from this intersection, we get something that's a topological space as well. It still has the structure of both of them, but there's a possibility, I must warn that there's a possibility that the Bussy set of some manifolds or F manifolds might forget some structure, you know? Especially this one. This case might forget structure. I didn't specify the atlas yet for the Mobius strip or the FT2 manifold. I mean, I definitely can specify this right now. I can write it on the board, but I don't feel like it. Or it's not necessary. I already wrote the atlas for FT2 in the last video. As for the Mobius strip, you can just search the parameterization for the Mobius strip, and then that's basically your atlas already. So there's a parametric equation that describes this manifold, so I don't need to write it down anymore. So the thing is, there's a possibility that when we take the intersection between both of these guys, we might forget some structure. Because notice how the Mobius strip only has one side. You travel along it, and then we travel both sides, so we technically have one side. But notice that a torus contains two sides. An inside portion, which is this thing you see outside, and then an inside portion, the thing that you saw inside the donut. So yeah, outside this circle over here, or this ring, which is like basically an individual ring among an infinite amount of rings that make up this torus. Inside the ring is some inside portion. It's like a cylinder, but we wrapped it around itself and then connected the ends. So a cylinder, and then we connected the ends, and then we get ourselves a torus. In fact, I believe that's how they construct toruses, or that's how the construction, or that's how Michael Penn proved. That's how Michael Penn proved that this construction, which is the complex numbers, mod the Gaussian integers, Zi, is actually a torus. Because he showed that through some abstract method, we first wrap the plane we wrap the plane first into a cylinder, like that. And then next, after we wrap it into a cylinder, we connect the ends to get a torus or a donut. And then that's how we show that this is isomorphic to R, and so it is a manifold, and so it's a donut. Though it could take some other forms, but topological speaking, it's a donut. It could be a mug or something, but it's really a donut. So yeah. Going back. Okay. Now that we've talked about Bussy spaces as a topological space, they're constructed between an intersection, from an intersection between two topological spaces that are either tangentially or directly related to the Bussy, right? Or to Femboys or whatever. So have F here, so a subset of our universal F. So I'll call it mathcal F1, equipped with this topology. And then take the intersection between that F1, or that subset, and another topological space, different one now. It can have different structure, but I suggest that it has the same, so you guys don't give yourselves a headache. Same topological structure, but different subset. Take the intersection of that, and then we get ourselves some Bussy space between these two subsets. I'll call this F bar 1, 2, and this is F bar 1. And then there's some Bussy set. The intersection is some Bussy set of F1, F2, as stated a while ago. Okay, so now, after thinking about Bussy spaces as some vector space, now let's think of it as as a topological space. Now let's think of it as a vector space. So you guys already know this. I talked about vector spaces in position theory already. And you guys already know it from your high school physics about what vectors are. But ultimately in pure mathematics, vectors are some object, mathematical object, an abstract mathematical object that's part of a vector space. But it is neatly described by physicists or your physics subject as some arrow that represents some force or some quantity, which they call vector quantities. Very fitting name. But we're going to think of femboys now as it's the vector. So position states. We already discussed this. We said that we know that femboys, or we stated through position theory that femboys can be some F1, some principal F, called Fn, can be broken down into some linear combination of other smaller femboy states or position states. So F1 plus beta F2 and then dot dot dot. And I think that's theorem 2, I believe. We can break down a femboy into linear combinations of other femboys. We know that. And since we can do this, we know that these guys are part of a space, right? They're part of a vector space, which let's call it VF1. Let's call it vector space of femboys 1. So one of them. And then now let's consider another vector space. So it's now composed of some Fi, sub I. So equal to some alpha I, F, say, not the same as this, but let's say Fj plus beta times Fj plus 1, and then dot dot dot. And let's say that this family is part of some second vector space, Vf2. Take the intersection between this vector space and this vector space. So find all femboys that are familiar or contain the same characteristics from this vector space and this vector space. And then those are what composes the Bussy space between this VF1 and VF2. So this intersection defines the Bussy set, or the Bussy space between VF1 and VF2. Now notice that this notation over here is redundant. You can pretty much switch the position of these two, and it would still be the same. Okay, it's not necessarily some ordered pair wherein the order of the two vector spaces matter. It doesn't matter, to be honest. Okay, so that's Bussy spaces as vector spaces. So we can just think of them as regular subsets, and that's the base case. The base case for Bussy space is that you're given two sets of femboids, right, or two sets that are tangentially related to the Bussy. You take their intersection, and you get a Bussy set. Now, okay, in summary, we can think of them as topological spaces, or intersections between two topological spaces, or manifolds maybe, depending on your topological space. If it's homeomorphic to R, right, to N actually. We want to say N. N is good enough for us to say it's a manifold. Then, well, yeah, take the intersection of those two topological spaces or two manifolds, and we get ourselves a Bussy space, or topological Bussy space. And if we have two vector spaces composed of femboids, or two vector spaces that are tangentially or directly related to the Bussy, and then take their intersection, we get ourselves a vector Bussy space. And yeah, I must say first that, well, if we have the manifold, really important property for manifolds is that we're able to map it onto REL. Okay, to abelian blocks also. We also need to let's discuss abelian blocks too. So this is the last theorem of this lecture, theorem 8. Theorem 8, two abelian blocks, which I will call A1 and A2, contain a Bussy set. If they are subsets of sets that contain a Bussy set. So suppose we already have two Bussy spaces here, or two femboid spaces, which these two abelian blocks are part of. So say a couple or a group of friends, we're able to map these two onto REL, like let's say how many people are inside the abelian block or abelian block. We can map that onto N and thus onto R. We know that, we can do that, and definitely we can show that these two are F manifolds, but that's our goal. Here, for the proof of this theorem, it's actually trivial. The proof of this theorem is actually trivial because all we have to do is say that, well, yes, they are. It's evident. It's obvious, or it's clear that A1 and A2 are part of some two sets that contain a Bussy set. So consider X, which is a superset of A1, and Y, that's a superset of A2. Okay, so consider the sets that they're part of. Okay. Now, we're going to show by contradiction that these two must contain a Bussy set, right? So let's say that X and Y do not have a Bussy set. Let's assume that there does not exist some Bussy set of XY, which is the intersection between XY. Then we have to consider, or we have to say, that A1 intersection A2 is not a Bussy set. not make this argument circular, okay, so, right. But we know that xy and a1, a2 are related to the Bussy. So we have to say, since they don't have some, well, if we have the axiom, right, we have our axiom of the Bussy set. If the axiom itself is right, the converse must be right too. So if we say that, well, two sets that are tangentially related to the Bussy contain a Bussy set, it must be that if two sets has a Bussy set, right, or two spaces have a Bussy set, then it must be, or Bussy space, then it must be that they are related to the Bussy. So if the axiom is right, or if we assume that the axiom is correct, then we must also assume that the converse is right. But the thing is, our axiom fails when we consider that two sets do not have a Bussy space, but they are. We know them fundamentally to be related to the Bussy. So they must have a Bussy set, but here we're assuming that they do not have a Bussy set. We're trying to say that, well, they don't have a Bussy set, and that we cannot. But the thing is, we already know fundamentally that if they are related to the Bussy, they must have a Bussy set. And so it contradicts with our axiom. So therefore, we must only assume, or that since we know that these four are related to the Bussy, or rather x and y are related to the Bussy, and a1 and a2 are related to the Bussy, it must be that they have a Bussy set. So that ends the proof. Proof by contradiction. Very popular way of proving things. So that's actually the end of this course. So I know it's been a grueling one, and you guys are probably banging your head against the wall about proving things in the problem set. So yeah, still accepting homework, by the way. We're accepting admissions. You just have to subscribe to the channel and answer one of our many homeworks in the course folders. I don't think I'm gonna make the course outlines anymore because you guys can just watch the videos. The videos are basically the course outline. So yeah. So that's it for this course actually, and thank you guys for sticking around this long. Honestly, it's a very grueling course. Honestly, most of our courses nowadays are very advanced, but I know you guys can pull through. So yeah, that's gonna be it for this lecture. And yeah, since this is my fourth course to complete, well, I'm already a general professor of mathematics here at LOSC, but yeah, I already taught 4 courses now that are somehow related to math, and it's a great achievement actually. I feel great that I'm able to do this thing, or I was able to do that despite a lot of roadblocks like not having enough ink to discuss and stuff like that, and even then. So yeah, I'm gonna rearrange the playlist so that you guys can see it better, and so it's later chat.
Hello
later. So yeah, I'm gonna fix the playlist, and so I'll see you guys in the next lecture. That was my friend.